Before I start the lecture, I would like you to put down your name, email address, and operating system for the Mathematica. So if you plan to stick around, I will give you a license to Mathematica. So please, in capital letters, name, email address, and operating system. Operating system, there are 3 choices. Linux, Mac, and the other one. Okay. That was announcement number 1. Announcement number 2, the schedule for the seminars is complete. It's online. If you're interested, check it out. Maybe I should first talk to the speakers. But anyway, we do not meet on the Thursday for the seminar. The seminar, not Thursday. But there is a regular class. A student of mine will run the exercise session. Today, the first assignment I've posted already. So we will talk about the first homework already in class today. But on Thursday, my student will cover it in more details. Okay, do you guys have questions? Otherwise, we can start. And I will start embarrassing myself. Okay, so let's try to go back where we left last week. So, last week, I made a mistake, so I admit it. What happened? I wrote something, and I asked you something. I wrote, we have 2 floating point numbers, and then I wrote that thing, and I said, how small can it be? Okay, that quantity is absolutely stupid. I wrote it, but that's not what I had in mind, because in my word, that quantity is meaningless. So I asked the question, thinking about a different quantity that I will show you in a minute. I asked the question, and a student back there tricked me because gave the right answer, but not to this question. He gave the right answer to what I meant to ask. And that's why I didn't realize that there was a problem here. Okay, what was the problem? I meant to divide. I meant to normalize this thing. Again, in my word, absolute differences are meaningless. That's why I didn't even notice that I didn't put the normalization factor. So the right question was, how small can z be if we normalize the difference? So, since I made a mistake, let's try to clarify. Otherwise, there is confusion. So, let's go with the stupid question, what I shouldn't have asked, but I did ask. So let's try to answer this question. What is the smallest z? Somebody immediately said, oh, it can be 0. Well, that's why now I have x different than y, so z cannot be 0. We all agree on that. So answer number 1 was the answer that I was trying to convince you about, which by now you know already that it's the right answer for a different question. So you know that answer number 1 is not correct. Okay. Let's look at answer number 2 or 3. Somebody said answer number 2 is clearly the correct one. What am I showing here? Basically, I'm getting 2 floating point numbers that are very, very close together, that are very, very small and very, very close together. And so what would be very, very small, we see from this factor, and very, very close together, we see from the fact that all the digits are 0 except for the last one. And so if I measure the distance between these 2 numbers, okay, this is their distance, and so somebody was saying that this is actually how small z could be. And while this is the mathematical distance, so while it's true that there are floating point numbers that are so far apart, it's also true that this number is smaller than the smallest number representable. So this would be an underflow. So this cannot be an answer. So z, as a result of this computation, cannot be this number. And the surprising thing is that nobody argued last week how to get the smallest possible number. Well, you take x to be 0, you take y to be the smallest possible number. The difference, that is not true. Okay. Yes, that is true. No, that is not true. I'm making the mistake again. All right, forget it. So this is actually the minimum z. What do you have to do? You have to basically take two numbers that are, again, that only differ on the last digit, but you have to shift the exponent by exactly t, 52 digits, so that then when you normalize, when you bring this one back here, we go back to the actual minimum representable number. Okay, so in light of these considerations, 1 is clearly wrong, 2 is mathematically correct, but it's not the number that you can obtain in floating point arithmetic, and 3 is the exact answer. Yes?
Wouldn't, if you do 2, the answer be rounded to 0? Because that's the closest number we can display using our floating point arithmetic?
No, actually, I think it depends on how the arithmetic behaves. I think you would get an underflow.
Yeah, of course you get the smallest denormalized number if you do it with double. But then again, you can get the number.
You should ask the IEEE people why they do underflows instead of zeros, or when they, if you look at the standard, it explains when it becomes a 0 and when it becomes underflow. No. That number you cannot represent.
What is that?
What's that?
The exact thing that number 2 is. And you can see down here the IEEE standard applied to the resulting double.
Yeah, it's probably denormalized, right?
Yeah, of course.
Yeah, okay. Okay, now let's go to what I meant to ask, which is part 2. And let's look at the same answers. So there was a lot of argumentation last week because you guys were trying to answer that question while I was trying to ask these questions. So clearly there was a little bit of a confusion. And now if you normalize, now everything goes well. So basically when you normalize, you divide by the exponent. So we would be in this situation, only that we divide by the maximum. So basically we cut the exponent, and so we go into the answer that I meant, the answer that I tried to convince you about. So what are the right answers? 3 for the first one, 1 for the second one. And I hope this clarifies the confusion from last week. Are there still answers? Are there still questions? No? Nobody argues? Okay. We like that. So professors do make mistakes, and you shouldn't take everything for granted, so feel free to argue. We looked at bisection, and the question over there was when or how to terminate bisection. Clearly, you cannot compare to 0, so you cannot set a while loop or a recursive function that terminates when the left and right are equal or when the function evaluates to 0. This will not work. You always have to talk in terms of thresholds. And as it was pointed out, this threshold should be normalized. So once again, it's important not to set an absolute threshold, but to set something that depends on the magnitude of the entries. The beauty of this fact over here is that even though the floating point numbers in the line are not equidistant, so as you move towards, so if you look there, I guess here, as you move towards infinity, they get further and further away, so they get larger and larger. Still, relatively speaking, the distance stays the same. So that's an important fact. Okay, we looked at this example, and I showed you in MATLAB that if you compute from if you sum numbers from the largest to the smallest, eventually you get to a point where the small numbers do not affect the solution anymore, and vice versa. If you start from the smallest and you go towards the larger, you keep adding some contributions little by little. So starting from the large ones, we'll get to more accurate results. And now we look at the solution of a linear system. We do some computation with this particular matrix. Let me copy the matrix. All right. What do we want to do with this matrix? As I told you already last time, when we have to do AX, when we have to solve AX equals B, we do not invert. This is a no. First of all, this is more expensive. There is just no reason to do this. It's more expensive, and it's much less accurate. So absolutely not. Instead, we compute an Alu factorization, and then we solve two triangular linear systems. Today, for the scope of this lecture, we don't care about the solution of linear systems. We just look at the computation of an Alu factorization. What is an Alu factorization? We start from a matrix A, and we compute a triangular matrix L, another triangular matrix U. L is lower triangular, and it has ones on the diagonal. So you can say that is unit diagonal or something along those lines, while U is upper triangular. Okay? So the goal is we start from A, we want to compute L and U. And we are going to do this for a very, very simple 2 by 2 matrix. Okay, 2 by 2 lower triangular matrix with ones on the diagonal. It doesn't have too many degrees of freedom. 1, 0, 1, and basically there is only L2, 1. That's what is left. And for U, U11, U12, U22. Okay, that's what I want to compute. So which ones are the unknowns? 1 L and 3 U's. So these quantities we have to determine. All right, let's see how to determine them. We know that L times U equals epsilon minus 1, 1, 1. But we also know, now we can multiply them together. This is A. We also know that this is U11. Then here we have U12. Down here we have L21, U11. And here L21, U12 plus U22. Okay. Questions so far? And now from this I have a number of equations. So I have 4 equalities. The first one tells me U11 equals epsilon. That was easy. Then second one, U12 tells me that is minus 1. Then we have L21, U11 equals 1, I think. And L21, U12 minus U22 equals 1 again. Thank you. Okay, so let's see what we are finding so far. This is a 1, this is a 1, and this is L21. Here, U11 is epsilon. Okay, we have it already. It's being computed. U12 is minus 1. Here we go. So now this is still missing, and then U22. L21 times U11 equals 1, so we know that U1 equals 1 over U11. U11 we just computed is epsilon. So we can replace this. L21 becomes 1 over epsilon. And now we can compute finally U22. 1 minus L21, 1 over epsilon. U12 we know that it's minus 1, so here we go. And the U22 is here. Okay, so we have computed our matrices. L and U. Okay, let me write it out. Maybe it's easier. Here's a 0. And here is a 0. All right. Now, let's say that we are working in single precision, or anyway, let's work with a small epsilon, and all of a sudden, if epsilon is small enough, this number magically becomes infinity. Yes, if it's exactly 0. Let's make it small, but not so small. Let's say 10 to the minus 8 or 10 to the minus 9. Yes, this thing becomes 1. Sorry. 1 over epsilon. So this is very small. 1 over epsilon becomes very large. 1 doesn't affect 1 over epsilon anymore. So this number becomes 1 over epsilon. What is the error that we commit? It's actually very, very small, very little, because we have a super large number here. Let's say 10 to the 9th, 10 to the 8th, and we only lose 1 decimal, the last unit. So the relative error, it's very, very small. So you wouldn't think that anything crazy could happen. But let's see what happens. If this happens, then let's just multiply our L and U back together. Let's see what happens. Epsilon minus 1, 0, and 1 over epsilon. Okay, this is, I haven't changed anything up there, so I assume that everything is still fine. Minus 1. I haven't changed anything here. It's epsilon over epsilon. So it's 1. And over here it's minus 1 over epsilon plus 1 over epsilon. So my final matrix is and I started from epsilon 1 minus 1, 1. There is 100% loss of accuracy. We add a 1, we find a 0. We add a 1 here. Okay, that's a 1. And we go back to 0. So we cannot reconstruct the original matrix at all. And once again, we only made a tiny, tiny relative error. And it has some disastrous consequences. Some of you could argue, well, it's one of those cases that you mentioned last week. The problem is ill-conditioned to begin with. So you just change things a little bit and you end up in a terrible situation. So let's see if the problem is ill-conditioned. Let's look at the columns of my matrix. Let's plot them. Epsilon, we said that it's going to be a small number. So epsilon 1 is the vector. Epsilon 1, pretty much like this. And the vector minus 1, 1. So now we go minus 1, 1 is like this. So you see the angle between these two guys. The problem is not bad conditioned, ill conditioned at all. You can plot the rows of this matrix and you find the exact same situation. The matrix is actually very nicely conditioned. If you compute the condition number, I haven't defined what the condition number is, but if you compute it, you will see that the matrix presents absolutely no problem. So what is the problem? The problem is a simply rounding error. We are dividing by a very small number, and so we change the magnitude of the entries with which we operate. The matrix has entries of the order of the unity, and we divide it by epsilon, and all of a sudden we go 8 orders of magnitude, 10 orders of magnitude higher, and so the unities are all entirely lost. What's the solution to this? The solution to this is called pivoting. But since I don't want to explain pivoting today, it's really not a linear algebra course. I just show you what happens if we take A and we flip the order of the rows. So now we have a A hat. And you might realize that if you're solving this linear system, swapping the order of the rows doesn't really affect anything as long as you also swap the right-hand sides. After all, you're just looking at equations. Swapping two rows means you are inverting the order of two equations, so it's fine. Whatever you do on A, just do it on Y. Nothing problematic happens. All right, let's compute the Alu factorization of this matrix here. The star is the same. We have 1, 1, L2, 1. We know already that U1, 1 is what sits here. We already know that U1, 2 is what sits here. So now we have to compute this is a 0 and U2, 2. All right, and we know that L21 times 1 equals epsilon. And we know that L21 times 1 plus minus 1 times U22 equals, oops, that's a plus, okay, equals minus 1. So from these I know that L21 becomes epsilon. Okay, so this is an epsilon plus U22 equals minus 1. So U22 equals minus 1 minus epsilon, I hope. Well, first of all, you see that now I don't have divisions. I don't have any crazy operation that changes the scale of the numbers with which I'm working. It doesn't matter how small I take epsilon or how large. Well, how large maybe yes, but it doesn't matter how small I take it. This operation is still well defined. And if you multiply these guys back, of course, you get the initial matrix. We can just do it. Okay, that's silly. So what did I do? I pivoted, and what in practice happened, I put the large numbers on the diagonal so that when I'm here, I divide by the largest number so that I keep all the quantities contained. In the previous case, I was dividing by a small number, so the quantities were exploding. And here, I tried my best to put the largest number here so that the quantities are contained. Okay. Connected to this, do you guys have questions? Yes.
What if E becomes very large? Do we have the same problem as before?
Okay, so if epsilon becomes very large,
And the minus 1 doesn't matter anymore.
okay, let's see. I think actually, okay. So you agree that this thing, if you multiply it, okay, let's see. So now epsilon is large. It's so large that minus epsilon minus 1 becomes minus epsilon. Okay? That's the question. All right, let's see what happens. So instead of minus 1 minus epsilon, we have that. So this is a 1. This is also a 1. This is an epsilon. And this is an epsilon minus epsilon, so it's a 0. Is it correct? Is that correct? So this is a 0 now. Yeah. So yeah, we are in trouble again. Yeah?
The idea of the technique was to put the largest number of the diagonal. If you now compute the upper one with a large epsilon, where we didn't do the whole thing,
Yeah, sure.
suddenly find that will work.
Yeah, absolutely.
So
That's now we would, if this is the case, the technique would be stupid. Because why did we put the 1 here? As I said, we want to make these numbers shrink, so we want the largest number to be on the diagonal. So if epsilon is the largest number, we should go back to our initial setting. In which case, okay. Now, in which case, we have a completely different story. This goes to 0, this goes to 0.
U22 is 1 plus 1 over epsilon.
Oh, yeah. This is a 1. Yeah, that would be a 1. It's here. So that goes to 1. So, okay, we can do the math again. Well, this doesn't have to be to 0. It doesn't have to go to 0. Wait, this stays 1 over epsilon. And yeah. So actually, this is perfectly fine. So there is no need to. That's exactly the story, right? It's the idea of pivoting. At each step, you always put the largest number on the diagonal. Of course, in a 2 by 2 matrix, you only have one step. If we have a 100 by 100 matrix, at each stage, you pivot, so you bring the largest number of the column on the diagonal, and you swap. You do one iteration, then you swap. But again, it's not numerical linear algebra, so let's not get into pivoting now. So last week we were talking about bisection, and we had something like left, right. We had some test, if, whatever, and then we had a recursive call, something like I don't know whom, but somebody pointed out that L plus right over 2 could give problems because L and right are floating point numbers, so that's perfectly fine. They lay in our interval, but L plus right, L plus R, maybe combined together go beyond the overflow limit. So, anybody has a better idea?
You start off with L, and you add to that half the distance to R.
Okay, instead of computing L plus R, I look at how far L and R are. So basically, I compute this distance here, which is R minus left, L. Then I divide it by 2. So basically, I have distance over 2. And then I say L plus distance over 2. And of course, this goes back to L plus R over 2. So these kind of little tricks can take you guys a long way. Don't ever take numbers for granted. So in your computation, pay attention to what can happen. If you're writing massive codes with thousands of lines, it's very likely that stupid things like this will affect the outcome of your computations. So pay attention to that. Okay. Questions? No. Back to the slides. I have one more test example. I think I will defer this until next week when I will introduce MATLAB. So for now, I just mention it. It's a comparison of square roots and squares. Which order you perform them, it might actually affect the computation. I will cover it next week. Okay, so far we have seen 3 different types of errors. Representation error, which is the error on the actual data. You have a number, pi, it has to be approximated. That's a representation error. Round-off errors. You have 2 numbers, even 2 floating point numbers, so numbers that are exactly stored in the computer, you add them together, like 1 plus 1 over epsilon. You add them together, and the result is not mathematically exact. That's round-off error. Then we have algorithmic errors. I showed you, we wanted to compute pi squared over 6. How to do that? Well, you have to add up an infinite number of terms. Clearly, we have to truncate at some point. So our algorithm is an approximation of the mathematical function. So algorithmic errors. In your code, most likely, you will have all of them. So far, everything seems tragic, but I want to spend a couple of slides to reassure you guys that actually things in practice are very well behaved unless you inject bad karma into your computations, or unless you are tackling an ill-conditioned problem. All right, first of all, I needed to define a machine precision. Somebody mentioned machine precision already last week. What is machine precision? Is this number, normally it's a bold u, bold small u, and it's defined in a number of different ways. For instance, those square brackets means that is a floating point arithmetic. So it means it's not a mathematical expression, it means it's something that is performed on a computer. Those are the square brackets. So how can u be defined? It's that number, the smallest number, such that when you add it to 1, the result is different from 1. You might think this is a crazy definition. Well, if you take a u that is small enough, it just disappears. We have seen before 1 over epsilon plus 1 equals 1 over epsilon. Right? Basically, we lost that plus 1. Likewise, if we choose a u small enough, 1 plus u stays the same, stays 1. Okay, we have a different definition, which is the largest number for which 1 plus u stays 1. Basically, we are defining the same number approaching from right and from left. These are different definitions for the same quantity. This is the machine precision for a generic base B. If you plug 2 in that beta, you find beta to the 1 to the power of 1 minus t minus 1, so 1 minus 1, beta to the minus t, which is actually that magic number that I presented last week, which is all the 52 digits 0 and the last one 1. That's it. In double precision, that is 2 to the 2.2 to the power 2.2 times 10 to the minus 16. Okay, it's also the distance between 1 and the next floating point number. And again, machine precision is called also machine epsilon. Sometimes it's represented with an epsilon m, sometimes most often with a bold u. Okay, why do we need this number? Because the IEEE arithmetic gives us some guarantees, all in terms of this u. So, representation errors. For instance, we have a guarantee that our numbers, even if we have a pi or the e or whatever other number, as long as we choose a number in between the smallest possible floating point number and the largest possible floating point number, any number, any real number in this interval satisfies this relation. We start from this number. X bar is the floating point. Which one is the x bar is the floating point number, the corresponding, and the distance between the true number and the floating point number is only a factor of 1 plus delta, and delta is smaller than the machine precision. What does this mean? It means that it doesn't matter where you pick your number, there is always a floating point number in a neighborhood, and how far it is, in relative sense, it's only 1 plus delta with a very, very small delta. This holds for numbers very close to 0, and it holds for numbers very, very large. Again, it doesn't matter where you are, as long as you are within the boundaries of floating point arithmetic, you know that there is a floating point number at a distance of 1 plus delta away from the exact number. There is also another result. Instead of multiplying, you divide by a factor of 1 plus delta. You can disregard that. Oh, what is important is that these deltas depend on the exact number. Okay, that was for the representation of numbers. Now let's look at the round of errors.
Sorry.
Yes.
It's very bad, but what did this slide want to tell me?
It wants to tell you that no matter, I told you that there are 3 types of errors.
Yes.
Representation error is the first one. And what the slide tells you is that no matter which number, which exact number you have, your computer will approximate it with something that is only 1 plus delta away from the exact number. It will never be the case that you have a floating point number so far that this bound is not satisfied. Okay? So even though these floating point numbers are not equidistant, even though there is only a finite number, there is a finite amount of them, you know that they are so tight that there is always 1 plus delta away from the exact number that you want to represent. Okay? And then there is another theorem for the operations. So these I said already, the square brackets are only a way of representing the computation in floating point arithmetic. So these you can read. Okay, the theorem says we want to perform x operation y. What are x and y? X and y are 2 floating point numbers. So these numbers have been stored in the computer. So now they are represented exactly in the computer. And my operation is something plus, minus, multiplication, division. So the result in computer arithmetic, in floating point arithmetic, the result of x op y is what, oops, there should be parentheses here, okay, just plot parentheses here. It's the result of what the mathematical operation returns, would return. This is the mathematical op, this is the computer op. These are the mathematical x and y, perturbed with an error, with a relative error of 1 plus epsilon. And what is epsilon? Once again, is smaller than u. This is a really, really strong result. It doesn't matter if you combine large and small numbers, as long as they are within the boundaries of overflow and underflow, this is satisfied. Means that your computer will make a mistake, but the mistake is relatively very, very tiny. Now also you see why I didn't even notice that I didn't normalize. There are never quantities in absolute terms. Everything is always in relative terms. Okay? Once again, there are parentheses here. There are even more properties like this. The square root is another operation for which these properties are satisfied, but of course square root, you don't have two numbers, so it's only square root of x, and you know that it's 1 plus epsilon away from the actual mathematical square root of x. And this quantity epsilon depends on x, depends on y, and depends on the operation. Like before, there is also another theorem that says that instead of multiplying, you can divide, but just disregard that. And you see epsilons are functions of the input data and of the operation. Notice that if you take two numbers, you put x1 plus plus y1, okay, you will have a certain error. Now you put a different x1, so now you put a x2 operation y2. The bound is still satisfied, but you get a different epsilon. The commonality is that all of these epsilon are less than the machine precision. That's why machine precision is so important. Questions? Yes?
But now it just have that we are most of the times fine.
Yes.
So we don't really we need to care about...
On one operation, notice that this is 1 plus, it's 1 minus.
And
It's
just because I have a lot of
yes.
and all the time I get a small,
Yeah, yeah.
just
Precisely. So the next slide is how these little operations combine together. So in the other semesters, I actually teach the error analysis, so I could cover this, but I don't want to spend the 20 minutes on the inner product. I just want to show you, we start from an inner product, x transpose y. What are those things? X transpose is a vector, row vector, y is a column vector, and I'm just multiplying, performing an inner product. So I spell out the operation up there. Down here, then I show how these 1 plus epsilon error terms actually show up and gather together. And down here, I represent the final result. So x transpose y, it's nothing more than chi I psi I. So this is an element of x, this is an element of y. So this is the actual mathematical solution. So far, so good. And all of this is the error term that comes together. And what is the error term? It's a lot of 1 plus epsilon terms multiplied together. This is the product of many of them, and so on. So whenever you do even very simple operations like an inner product, immediately you see that the result is contaminated, is perturbed by a lot of these 1 plus epsilon terms. Okay? So those are your enemies. But I don't want to discuss these things. Now, when it comes to the algorithmic error, I put a slide for you guys. Please read it. I feel bad if somebody finishes my lecture without at least having heard what backward stability is. On the other hand, it has nothing to do with languages, so I don't want to kill you guys with this, but please at least read it. As part of the exam, one of the questions will be, have you read about stability analysis? And then I will read your soul and I will know if you're lying or not. Okay, references. IEEE standards. This has been revised recently. The first two are documents that define all of the properties and many, many more properties about floating point arithmetic. The Bible for stability analysis is Nick Iam's book, Accuracy and Stability. This article actually covers most of what I have told you guys, what every computer scientist should know about floating point arithmetic. There is a nice book by Michael Overton. Then there are Valvo Khan in Berkeley. He pretty much is the god of floating point arithmetic. If you know what, okay, everybody knows what a Nobel Prize is. The Turing Award is the equivalent of a Nobel Prize for computer scientists. There is no Nobel Prize in computer science. So this guy, Valvo Khan, is a Turing Award for his work on floating point arithmetic. So if you want to know more, probably that's the guy to talk to. Okay, at this point, if you guys don't have questions, do you have questions? If you don't have questions, I pass, I move on to the assignment. So we discuss the first homework. So we have some time to describe the homework and to give some examples. Part 1, it's just a few questions on floating point arithmetic. We don't have to discuss this now. Just look at them at home. On Thursday, the exercise will be on floating point arithmetic. So I suppose that you will find these answers on Thursday, or maybe you will find something that is very close to this. Instead, I want to look at a programming assignment. After all, the class is on the languages, so this is the first programming assignment. All right. You take a look while I erase the board. Okay, is it clear so far? You understand what I'm saying? We have a matrix A, size n by n. It's large. It's so large that it takes 4 computers to store it, 4 processors, okay? And how is it stored over these processors? Well, it's divided into 4 quadrants. And each processor, let's move this guy, that bothers me. And each processor starts off with one of these quadrants. So P0 owns the A top left part of the matrix, P1 owns A top right, and so on. And then I have these nice little matrices, B and C, that are defined in terms of A. In fact, B is defined in terms of A, and C is defined in terms of B. Okay? And I want to compute C. Questions so far? You should have some questions. So you have to come up with an algorithm for computing C. Nobody has questions? Okay, guys, let's look at what happens. B top left, let's see what it is like. B top left is the sum of A top left and A top right. A top left is a matrix that sits on P0. A top right is a matrix that sits on P1. So these 2 processors, they better communicate, they better exchange some data, otherwise A top left plus A top right is not going to happen. Do you agree with me? Yeah. So maybe we should talk about how these processors can communicate, what kind of instructions they are allowed to execute. And that's the next slide. Instruction set number 1. Here I specify how these processors communicate, how they exchange data. I say that they exchange data by means of two instructions, bsend and breceive. And then they have a third instruction, basically to synchronize, if they need to. For those of you who are familiar with MPI, these are pretty much the standard send and receive from MPI. But don't think about MPI, just read the definition. Everything is spelled out here. So what is the semantics? What is the meaning of bsend? Bsend is a function that takes a variable name, var name, takes a j, a processor number, and a tag. Tag is just an ID, an identifier. And what it does, actually doesn't do anything until a corresponding receive is executed by the processor j. So what I describe here are instructions that the processor I, see, I say these instructions are available on processor I. So processor number I can send something to processor number j. And I'm telling you that this send doesn't go through, so nothing happens until processor j here issues a receive. Okay, not only does j need to issue a receive, but it has to have the same tag. So when I says I send data to j with tag number 100, and then j says I receive data from I, at this point it is from I, with tag number 99. Oops, he's sending on tag 100, he wants to receive on tag 99, nothing happens. But if the tag is 100, okay, processor I wants to send to processor J wants to receive from processor I, the tag number is the same, the data is actually transmitted. Okay, this is the semantics. And I explain exactly what two-sided means. Two-sided means that the communication only happens if the send and the receives are posted together, okay? I also say that the communication is blocking. So processor I, if he wants to send before the receive has been posted, it just stalls. It's there waiting until the receive is actually issued. Vice versa. If the receive is issued before the send is posted, processor J is sitting idle until the send is posted. Okay, finally synchronization. Synchronization is easy. If a processor issues a synchronization, it just stalls, it sits idle until all the processors post a synchronization. At that point, when all of them have posted a sync, they all move on and continue with whatever the next instruction is. So now, given this instruction set and this setup, the objective is to write a program to compute C. Questions so far? Yes?
Would you prefer a single program that uses the ID of the processor it runs on, or four programs that just have everything?
That's a very good question. Wait 2 more slides and I will answer that. Other questions?
So the idea is that we use MPI for this program?
Don't think MPI, just think bsend and breceive. But yes, the concept is that you have different processors, you have to write a program for these processors, you have to specify what kind of communication is needed for C to be computed.
So we're just talking about pseudocode, not a real program. Because
Yes. Absolutely. I specify these in 2 slides. Okay, if you guys are clear with this, the second part is much more challenging. We go to instruction set number 2. So instruction set number 1, remember, was two-sided. So send and receive, they have to be posted. And blocking. Once you post the send, you wait until the receive is posted and vice versa. And now we go on the other end of the spectrum, and we go into one-sided and asynchronous communications. So we have a get. Again, this is available on processor I. So get, what does get do? It takes a variable name of a variable that is not local to I, is actually a variable that is local to J. Okay, it's going to go into J's memory and fetch some data from there. J is the processor from which to steal the data, to get the data, and tag is the same as before. Okay, the communication is one-sided. It means that processor I goes and fetch stuff, data from processor J without J doing anything. J is just doing his computation, and some other processor goes into his memory and reads some stuff and takes it back. Okay, it's one-sided. There is no participation of processor J. This can be very nasty and tricky. Also, it's asynchronous. What does it mean? It means that processor I issues a get, and maybe he wants to get a lot of data, maybe he wants to get a really large chunk of a matrix. Well, this communication takes time, but I doesn't wait. As soon as it issues this fetch, it just continues. The program continues. So if in the program you have a get variable whatever from processor whatever, and then it says print, you will see the print, and this does not mean that the communication has completed, okay? So how do you know when the communication has actually completed? Well, with the complete statement. The complete is synchronous, is blocking. When you say complete on this number, okay, the program actually stops until the corresponding get of this tag completes. Okay? And then we have, again, a synchronization to synchronize. Synchronization here is the same as before. So now we are on the complete opposite end of the spectrum. Two-sided and blocking, and now here is one-sided and non-blocking. Yes?
How do you deal with deadlocks here?
Ha! You have synchronizations. Yes?
How do we ensure that J, who just doing his stuff, doesn't touch the memory during I is getting...
Very good. You're asking the right questions. That's the assignment.
Maybe you just can say, wait until some flags there, but this is not what we want to do, because I think I should work because it's more efficient.
Yes. So now I can go into what you guys are supposed to do. Assignment, and by the way, this is a challenge. Remember challenges? So we will decide who has the most elegant code. So there will be a winner. What do we want? What do I want you guys to do? And this answers your question. Either you write programs for all the 4 processors, or you write one single program, parametric. What does it mean, parametric? It means that you write the program for processor PI, and when instead of the I you put a 0, the program magically works for processor 0. When you put 2, it works for processor 2, but you only wrote one program. So it's up to you. Keep in mind that the objective is elegance. And as I said, okay, with point number 2, use your favorite meta pseudo language. What does it mean? You don't have to use something that actually exists. You can make up your syntax. You can make up your rules. This is a possibility for you to actually express your elegance also visually. So we want something that, we want to look at a code that actually explains what's going on. Or maybe it doesn't, but it's elegant anyway. I don't know. And as you said, yes, of course we want performance. So try to minimize the number of synchronizations. It's easy to make this program work, just synchronizing like crazy, but you want these guys to run free, so minimizing number of synchronizations. Of course, point number one is that the algorithm has to compute the right thing. And I promise many of you will not submit a correct algorithm. Whenever there are deadlocks, whenever there is parallelism, it's very easy to get things wrong. You just look at it, you think everything is going to work fine, and inevitably there are situations where deadlocks occurs or things like that. Okay, 2 parts, instruction set number 1, instruction set number 2.
We do them separately.
Yes, separately, yes. Submission. So, since I had headaches in the past years, now I decided to automate the submission process. So please follow the rules, and everything will be will just be handled automatically. So submission by email to me. This is an individual assignment to begin with. Then there will be team assignments later on. Yes? Yeah, rock on. Thank you. So 2 mistakes, parentheses and hat missing. I will fix them. I will fix both of them. Okay. Yes?
So the code, our solution don't have been in a language that a compiler exists.
Sure, it doesn't matter. As long as the language is sound, I'm perfectly fine.
So you just want, okay. You don't want a program. So
Yes.
You want just one code.
You confused me with that one.
Can I just paint a picture, or how do you...
No, wait. I want to see how you use the gets, the completes, the synchronizations. I want to see how you use the sends, the receives, and there has to be the computation. So I want to see the pluses and minuses and everything, okay? But I'm not asking to write it in C. I'm not asking to write it in any specific language. You can make up your own language. I saw another question. No? Okay. So maybe since we have time. Yeah. Since we have time, oh yes, we have a question.
So about the time, you said on Thursday there will be the exercise. Do you need 1 week?
This Thursday. In 2 days there is exercise.
But we don't talk about the second part of the assignment?
No. The exercise is strictly on the first part. If you want to talk about the second part, we have 20 more minutes today. That's what I'm trying to do now.
Do we have to submit anything for the first part on Thursday?
Not this Thursday. Everything is, even the first part, floating point arithmetic, you just put down your 5 answers in a PDF, in a PostScript, or in a text file, and you send it together with the programs for this. Okay? So, since we have time, maybe I can give you a little example. Okay, let's say that we want to compute the same operation as before. X and Y are vectors. Okay. Alpha is a scalar, of course. And so let's say that we have 2 processors, P1, P2, and we need to make the problem interesting. So let's say that the memory available is So, what does it mean? The vector x sits in P1 and the vector y sits in P2. And what do I have to do? I have to multiply these guys together. Unfortunately, none of the processors, neither one, has enough memory to just get the full vector and do everything at once. So we need some cooperation. I thought there were, okay?
We start off by issuing a p-send on P1, which sends, say, the first half. One
second. So we're now considering the program from the eyes of P1. And you are suggesting to do a send.
And we're going to send, say, the first half of our vector, which is x. And obviously we're going to send it to P2.
So you want to send the first half. You want to send it to P2.
Right.
Now, to make the drawing clear, each processor has the initial vector and also has some other half of a vector available. I said that as memory I have 3 halves. So this is 2 halves, and then there is a free third half. So what you're suggesting is to do a send that will go here.
Correct.
So I just say first half of x to processor 2. Okay?
And we have to add some tag. We can just use 1 here because it's the first number that I make off.
Okay.
And P2 starts with a similar program that essentially just does the receive part of this transmission. Receives something to its buffer. I don't know how we want to call it. So it receives 2 QMP. And of course the processor from which it receives
Yes.
1 and
Okay. So under the description of the instruction set number 1, we have a processor 1 that executes this program, and we have processor 2 that executes this program. We don't know if these 2 guys start at the same time. We don't know that. But we know that P1 will issue this send and will stop. It stops until P2 issues these receives, or vice versa. P2 issues the receives and stalls, it's idle, until P1 issues that. Yes?
The first question is that does it send it as a copy or just releases the memory?
Okay, that's a good question. It sends a copy. Keep in mind that these 2 things are different computers. Okay, so that's...
Question about the homework assignment then.
Yeah.
Do our processes also have some kind of buffer available?
Yes, it's good. It's good that you mentioned. That's exactly. So you ask, not here. Each processor has enough local memory to store exactly 2 matrices of size n over 2 times n over 2. What does it mean? Each processor can store 2 of these blocks. And notice that we start off with one of these two blocks taken already, because processor 0 owns a top left. A top left is of size n over 2 times n over 2. So one of these two matrices is taken. And you better do a good job with it, because that's the original data. That's the input data. So now you have another matrix, a small matrix, that you can play with. Yep? Okay? All right, so you guys, I think this is enough. I can give you a hint for, now we go way forward. Hint for the exam. Not for the assignment, for the exam. What you will work on is two-sided synchronous, okay. One-sided asynchronous. So notice that if it's one-sided, it could be a get, which is what you have to do. But hey, it could even be nastier. It could be a put. Put is even nastier. So how is that? You're working on your memory, and now some other processor, without you knowing, comes and writes in your memory. Okay? So get, at least you read and you copy it, and you know what you're doing. Put is possibly even worse, because you are invading somebody's privacy. You're just writing things. So if by accident you don't do a good job in this assignment, maybe at the end of the semester something along these lines could actually turn up. Okay, that's a suggestion. Just, you know, if you're having a tremendous fun with these assignments, think about put as well. It's just fantastic. It's fun. All right. Questions, guys?
What does it write the solution see? Is there space in the memory, because since it has when we get the communication?
The solution has to sit in one of these two matrices. So in the end, you will have to tell me where the solution is. As long as you have this much space, you use it so that at the end of the program, part of this space contains the solution. And you have to tell me where it is. Okay? Okay, so just as a brief history, the one-sided asynchronous communications is not just the product of some crazy programmer or mad scientist. If you have ever heard of a PlayStation, inside a PlayStation there is a cell processor. The cell processor uses one-sided asynchronous communications. And I was one of the unlucky users or programmers of the cell processors, so I have coded, I have extensive experience with these beasts, and I promise it's really difficult to keep them down, to tame the beast. The two-sided synchronization, of course, the two-sided communication, of course, it's MPI. MPI has a whole set of different two-sided communication styles. So in MPI you have synchronous and asynchronous two-sided communications. And well, you can do all sorts of two-sided types of communication. One-sided is much nastier. Okay, if you don't have questions, I will see we do have questions.
Can we assume that a matrix multiplication is far slower than network latency and synchronization and whatever?
Okay, so matrix multiplication is fast.
Fast law, because we have all those multiplications to do. But it really depends on what machines you think about. If you have
Yeah,
machines that
do not make assumption on the speed for this assignment. So sometimes as a second assignment I ask questions when we make assumptions on the ratio between the speed of a computation and the speed of the communication, but I don't want to look into this, at least not at the beginning. So don't assume anything about speed of computation or speed of communication. Okay? I will see you guys next Tuesday, and oops, no, two things. So next Tuesday, we will start MATLAB. As everybody put down his name or her name. Yeah, everybody? Okay. Thank you, guys.